And good afternoon. I am Tracy Sinclair here at Alaska's News Source. And you know, we talk a lot about the Aurora, love to see the Aurora, but there is a lot of study that goes on around the Aurora. So I thought today we would take a little bit of time. Oh, let's see. There we go. I don't think my mic was up. I've done that again. Here we go. I'm Tracy Sinclair with Alaska's News Source, and today we are talking about the science of the Aurora and why we study it, how it can impact us. And so to bring in an expert, we are talking today with Don Hampton. He is with the University of Alaska Fairbanks Geophysical Institute. Don, thank you so much for joining us. Now, can you give me an idea, why do we actually study the Aurora?
So the aurora impacts a layer of the upper atmosphere we call the ionosphere. If you know any ham radio operators, they already know about the ionosphere because they deal with that all the time. The frequencies they deal with, the radio waves might skip off the ionosphere and they might not skip off the ionosphere. So they're always interested in that. But it certainly impacts any sort of radio frequency that's traveling through the upper atmosphere. Say if you're talking to a satellite, or if you're receiving satellite signals like your GPS receiver, or if you want to talk, on a HF radio to an airplane or whatever, sometimes you get funny skips. So it's always sort of been about communications. But the other thing that happens is when aurora is happening, we also get very, very large currents in the upper atmosphere in the same ionosphere region. And those large currents, I don't know if you remember, when you're at grade school or high school physics class, if you drive a current through a wire, it actually creates a magnetic field. And when that magnetic field interacts with, say, power lines or pipelines, it can actually induce large currents in those structures as well. So those are two of the main things we're worried about. And more recently, we're kind of interested when you have a bright auroral display, that's putting energy into the upper neutral atmosphere, and that neutral atmosphere actually expands and contracts as you heat it up. And that can actually affect the orbits of satellites. The satellites can change their orbit just slightly. Now that we have lots of satellites up there, we're always worried about whether they're going to get close to each other. And so a slight change in an orbit can have long-term impacts on trying to keep satellites from impacting each other.
And so when you how do you study them? I know we've done stories here at Alaska's News Source. We've shot rockets. You guys have shot rockets into the Aurora. But how does someone actually study the Aurora? Because it seems, obviously for us, most of us, it just seems like pretty lights in the sky. How do you actually study the Aurora?
Yeah, so the easy way to do it is just to have ground-based instruments. And of course, the workhorse for many years has been cameras. The nice thing is cameras have gotten more and more sophisticated. I mean, the picture behind me was, it's a picture I took with just a camera I bought on a shelf somewhere. So it's been really nice. But the same thing has happened in scientific cameras. And so we can get very, 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 very sensitive cameras now that can measure the aurora quite precisely. But we also have instruments on the ground using radar techniques that can measure how dense the electrons are in the upper atmosphere in the ionospheric region when the aurora is happening. We can also even use GPS receivers. If we have a specific kind of receiver that receives two different frequencies on the GPS, which it's producing all the time, it can make specific measurements to look at how the aurora affects the upper atmosphere as well. So those are ground-based things. And like you say, sometimes we'll actually use high-altitude balloons. They don't get into the aurora, but they give above most of the atmosphere. So you can use cameras at different wavelengths, like ultraviolet or infrared, to do that. I'm working on a project now with another group to do some of that. And then, like you said, we can launch rockets up and over the aurora. That looks at the particles that are creating the aurora, and also the electric fields and magnetic field changes associated with that. And then there is also have been a series of satellites that are always orbiting the Earth, and many of those have instruments that can make direct measurements inside the aurora as it's being produced.
And so while we talk on this next question, I am going to play a little bit of video from one of our viewers that sent us some video in of the aurora that they took. What makes the different colors that we see in the atmosphere? Is that what is causing those different colors that we're going to see up there?
Right. So the aurora is created by these high energy electrons that come down from our magnetic field, a region called the magnetosphere. That's where our magnetic field dominates, the Earth's magnetic field. when they come down, they're very much they're acting very much like what happens in a neon sign. And what happens in a neon sign is you drive electrons through a gas, they bump into the gas, either atoms or molecules. And when they do that, they excite those atoms and molecules. And when they sort of relax, what they send back out is a little bit of light. And we call those photons. It's just a light. The colors are based on sort of the internal structure of the atoms or molecules. Because they're all a little bit different, they all have different colors. So the green that you see, that's usually the most dominant color that we see when we're taking pictures of aurora. That's from atomic oxygen. Now that's different than the oxygen we have down here, which is molecular oxygen. But at those altitudes during the daytime, solar UV can break apart the O2 into the individual atomic oxygen. And so we're seeing that. And then sometimes on pictures you see on the top of auroras, you see this really sort of brilliant red. That's also an atomic oxygen. And then when you get the really, really active aurora and you see those sort of lower borders that are different color, you can see a little bit of it over my shoulder there. That sort of pinkish red lower border is emissions from nitrogen. So that's N2 like we have down here in the troposphere.
So I have a video from that. I'm going to play it. Bruce Nelson sent us this video of from Kotzebue, just taken last winter. And so really an amazing version where you get to see not only the greens, but the purple and that bright white. And so it looks like it's in our atmosphere. Is this above our atmosphere?
Well, so our atmosphere just gets thinner and thinner the higher you go. And so, yeah, it's our atmosphere, but it's, it's about 60 miles up. Those pink layers are 55, 60 miles above us. So, I always say here in Fairbanks, if you turned your car and drove straight up, it would take about an hour to get there at 55 miles an hour. It's like driving to Manana from Fairbanks. So it's way up there. So the atmosphere is very, very thin. But you got to remember these arcs you're looking at are a couple of miles wide and they stretch several hundred miles long. It's always impressive how large these structures are. But that's a great example of really energetic particles. And when they've got a lot of energy, they can penetrate further down. And like I said, they're bumping into the nitrogen that tends to dominate a little bit lower altitude than the oxygen.
Yeah, that's one of my favorite videos that we've gotten from a viewer. Just you can see how active the aurora are, and it's not sped up so many. We do watch a lot of time lapses, which I love. One more question. Sometimes when you look at the Geophysical Institute's website, there is that aurora forecast, and it goes out to about 30 days. How far out can you forecast the aurora, and how accurate is it? I mean, does it change when you get closer to a date?
Well, there's sort of 4 time scales we can deal with. One is called the solar cycle. So the sun, every 11 years, the magnetic field on this inside of the sun actually reverses itself. And as it's reversing, it gets sort of more chaotic on the surface. And that's when you see things like sunspots. And that's when these coronal mass injections start happening. These are these solar storms that we often see during the solar maximum periods. So we sort of know every 11 years it's going to be really good. And then, the next 5 or 6 years, it's going to be kind of quiet. So that's one big prediction. Now that, if you're planning a trip to Alaska, that doesn't say you should be Tuesday the 3rd in March, something like that. So the next one is that the other thing you can do is look at the sun. Like I said, the sun is the source of all the energy that's creating the aurora. If you had good conditions on the sun 27 days ago, it's very likely you're going to get another period when you're going to have good aurora about 27 days later. So that's the period it takes the time. That's the time it takes the sun to rotate once. So if there's a hot spot, it's likely to come around again, and there's a good chance you'll get something at that time. The other one is we've got satellites watching the sun all the time, and they can see these sort of explosions off of the sun. We call them coronal mass ejection because it's particles that come out of the corona. And we've got several satellites that can sort of what we call triangulate. They can look from different directions and see which way that storm is coming. And if it's coming right at us, then the NOAA will actually put out a warning saying we might have a solar storm. So that's that sort of. And I should go back and say that takes about 2 to 3 days for those particles to get from the sun to the Earth, depending on the speed, but anywhere from about 2 to 5 days. So we sometimes we'll have a warning on that kind of time scale. That's something you can look at the Space Environment Center at NOAA. And then we also have satellites that sit in front of the Earth at what's called the Lagrange point. That's where the magnetic, the gravitational field of the Earth and Sun sort of match each other. And when they're sitting there, they're about 1 million kilometers ahead of the Earth and the solar wind, and so they can actually watch the solar wind coming in toward us, and they give us about an hour of warning. So very often, when we're waiting to launch a rocket, we'll be watching those satellites measuring the solar wind in real time. And if we see the right conditions there, it speeds up and the magnetic field turns in the right direction, then we'll get ready to think about launching at that point. So sort of 4 different time scales you can deal with. One is 11 years. Well, that's that's a long-term planning. About a month ahead is a good thing, and the 3 or 4 days usually pretty good. If they can get the direction and the speed of that storm coming, they can tell you pretty well. As to the accuracy, obviously the 27-day is not super accurate, but it sort of trends to be better. It'll tell you sort of in general in the next 3 or 4 days. It's likely to be better if it was good about 27 days ago.
So we had I think it was forecast to be a 6 a couple of weeks ago. Unfortunately, it seemed to be happening during daylight. So, we didn't get to see it.
Yeah, the sun doesn't always cooperate. Sometimes it lands when it's dark in Scandinavia and we don't get to see the show. So that's unfortunate.
Well, Don, I want to thank you so much for being here. Don Hampton is a research associate professor at the University of Alaska Fairbanks Geophysical Institute, doing a little bit of information here just to kind of help educate us a little more on the Aurora, because we love the Aurora so much. And I want to thank all of our viewers who have sent us videos. If you would like to send us your videos or pictures of the Aurora, there's a really easy way to do that. All you have to do is go to alaskasnewssource.com, and you will be able to find a little link on the upper corner that says submit photos and videos. And we would love to see your photos. We'd love to see your videos of the Aurora or anything that you see in the night sky. I know we've got some meteor showers going on over the next couple of months as well. Thank you again, Don. Thank you all for joining me. We'll be back next week with something new in the Alaska skies.